All right, in this final section, we're going to look at some problem solving as it relates to buffers. Here's problem 1, buffer pH after adding base. A buffer is made by adding 0.300 moles of acetic acid and 0.300 moles of sodium acetate to enough water to make 1 liter of solution. The pH of the buffer is 4.74. Calculate the pH of this solution after 0.020 moles of sodium hydroxide is added. The Ka of acetic acid is 1.8 times 10 to the minus 5, and we can assume that any change in volume is negligible. All right, so the first step or the first phase in the problem solving is the neutralization stoichiometry. Was a strong acid or a strong base added, and which component of the buffer will neutralize the added substance? In this case, a strong base was added in the form of 0.020 moles of sodium hydroxide, and that strong base will be neutralized by the weak acid, which is the acetic acid, 0.300 moles of acetic acid. Then we're going to write the relevant dissociation equation and create a chart using the concentrations of acids and bases from phase 1. Remember to add the corresponding amount to the original base as was subtracted from the acid. Okay, so here's our dissociation of our weak acid to weak base or a conjugate base. And then before the neutralization occurs, we have 0.3 moles of our acid and 0.3 moles of our conjugate base. And before any neutralization occurs, we have 0.020 moles of sodium hydroxide. Then all of that is neutralized by the acid. So the acid is consumed, okay, 0.02 moles of it. It's consumed by the creation of the conjugate base. So we would expect an increase there to a final number of moles of 0.32, okay? The highlighted values are the moles after neutralization of the added base. Since the volume of the buffer is 1 liter, the number of moles in this case is the same as the molarity. The second phase here is the equilibrium calculation. So once we know the number of moles after the neutralization occurs, we can find the concentration and use the dissociation equation and the Ka value to calculate the pH. All right, so given that dissociation equation, the Ka value, which is given as 1.8 times 10 to the minus 5, is the concentration of H3O plus times the acetate ion over the acetic acid. I'm substituting these concentrations from the previous slide. This is the acetate ion, which increased, and the acetic acid, which decreased, and then the hydronium ion concentration, which is unknown. Solve for that unknown and get 1.58 times 10 to the minus 5, and use that to find the pH and get 4.80. Alternatively, you can use the Henderson-Hasselback equation to calculate the new pH, where it's equal to the pKa, or the minus log of the Ka, plus the log of the base concentration over the acid concentration. So remember, this is the A minus, or the acetate, over the HA, or the acetic acid concentration. And I just want to point out again, in this problem, we found number of moles, but it's in a 1 liter solution. So moles per liter, the moles and the concentration would have the same numeric value. So then the pH in this case is 4.80, which is the same result we got using the equilibrium expression on the previous slide. Problem 2, buffer pH after adding an acid. A buffer is made by adding 0.140 moles of cyanic acid, HCNO, and 0.110 moles potassium cyanate, KCNO, to enough water to make 1 liter of solution. Assume volume changes are negligible. Ka for cyanic acid is 3.5 times 10 to the minus 4. A, calculate the pH of the buffer. B, calculate the pH of the buffer after the addition of 0.018 moles of strong acid HNO3. All right, so first calculating the pH of the buffer. Since the total volume is 1 liter, the number of moles equals the molarity. So keep that in mind throughout this problem. The Henderson-Hasselback equation can be used where the pH is equal to the pKa, the minus log of the Ka, 3.5 times 10 to the minus 4, plus the log of the base concentration over the acid concentration. So in this case, HCNO in water produces H3O plus, and the CNO minus. So this is our acid, this is our base. So HCNO is 0.140. So for the acid, we have 0.140, and the base is 0.110. All right, so then just finishing this computation, we get a pH equal to 3.351. All right, so in part B, calculate the pH of the buffer after the addition of 0.018 moles of HNO3. So the strong acid will be neutralized by the weak or the conjugate base that's in the buffer. So the neutralization reaction looks like this. CnO minus plus the addition of this strong acid, which is H plus, will produce that weak acid that's in the buffer, HCNO. So these before amounts, these initial amounts are given in the problem. We start with 0.110 moles of CNO minus and 0.140 moles of HCNO. And then we start out with all of our strong acid, 0.018. Now, all of that is neutralized by this base, leaving behind 0.092 moles of the base. In doing so, we produce the acid, so we increase that amount to 0.158. Keep in mind, the moles are equal to the moles per liter in this case. So we're going to use these as our concentrations in subsequent steps. The next step, once the neutralization occurs, is the reestablishment of the equilibrium. So here's our dissociation reaction for us to talk about the equilibrium. So initially we start out with those amounts that we calculated from the previous slide, and remember, all of this is consumed, so we don't have any of that. Some of this will dissociate and produce our products, leading to equilibrium concentrations as shown. Now, we could put these into a Ka expression and solve for x, assuming that the change is very, very small. Or we can use our Henderson-Hasselback equation, where pH is the minus log of the Ka, 3.5 times 10 to the minus 4, plus the log of the base concentration, which is here, over the acid concentration. Remember that this is so small that we can assume negligible, and the initial and equilibrium concentrations would be the same. And in that case, we get a pH of 3.22. Problem 3, buffer pH after an acid or base are added. A buffer is made by adding 15 grams of ammonia and 55 grams of ammonium chloride to enough water to make 1 liter of solution. Kb for the base is 1.8 times 10 to the minus 5. A, calculate the pH of the buffer. B, calculate the pH of the buffer after the addition of 0.013 moles of HClO4, strong acid. C, calculate the pH of the buffer after the addition of 0.015 moles of KOH, or strong base. First, let's calculate the pH of the buffer. So we know we have 15 grams of ammonia, which is 0.0882 moles in 1 liter, gives us a concentration of 0.882 molar, and 55 grams of ammonium chloride, which is 1.02 moles in 1 liter, 1.02 molar. And we know the Kb. Since this is a weak base and salt buffer, so we have the weak base and a salt containing its conjugate acid, we can use the Henderson-Hasselbach equation for bases, where POH is pKb plus the log of the acid concentration over the base concentration. So in this step I've just substituted. The acid is 1.02 molar, the base is 0.882 molar, and we get a pOH of 4.80 or a pH of 9.20. All right, so now what is the pH after the addition of strong acid? 0.013 moles of strong acid. The strong acid will be neutralized by the base. So the neutralization reaction looks like this. NH3 plus the H plus coming from the strong acid is neutralized to produce NH4 plus. So here's what we start with. 0.882 moles of NH3, 0.013 moles of our acid, and 1.02 moles of our NH4 plus. Now, all of this is neutralized. So we use all of it up. We're left with 0.869 moles of NH3, which is also the molarity because we're in 1 liter, and 1.033 molar NH4 plus. All right. Once we know the initial amounts that we're starting with after the neutralization, we can complete this equilibrium calculation. So these are the initial amounts after the neutralization. Initial amount of NH3 and NH4 plus. Now some of this will dissociate, so we'll decrease by X and then increase each of our products by X. Keeping in mind that this change, this X, is very small relative to the initial amount, we will ignore it in our concentrations. Now, we could use the Kb expression for NH4 plus and OH minus over NH3, assuming that OH minus is X, to solve for X, and therefore the pOH and the pH. Or we can use the Henderson-Hasselback equation. pOH is pKb plus the log of the acid over the base. So the minus log of the Kb, which is given as 1.8 times 10 to the minus 5, plus the log of the acid, 1.033 over the base, 0.869, gives us a pH of 4.81 or a pH of 9.20. In part C, let's calculate the pH of the buffer after the addition of 0.015 molar KOH, which is strong base. So any addition of strong base will be neutralized by the ammonium chloride, the NH4 plus, to produce the weak base NH3. So before any neutralization happens, we have our initial amounts. All of the strong base is neutralized. So the NH4 plus decreases while the NH3 increases. And from there, we can find the pH. So I used the Henderson-Hasselback equation to say pOH equals pKb plus the log of the acid over the base. These are the concentrations we calculated in the previous step. The Kb was given in the problem. And we get a pH of 9.2, which is exactly the same as calculated in parts A and B, which is to be expected because that's the point of a buffer, is to resist those changes in pH. Keep in mind, I did put the equilibrium ice chart here just to remind you that you could use a Kb expression to perform this calculation as well, solving for X and then solving for the pOH and pH that way. Problem 4, calculating pH changes in buffers. A buffer is made by adding 25 grams of ammonia and 45 grams of ammonium chloride to enough water to make a 1.75 liter solution. Assume volume changes are negligible. Kb for ammonia is 1.8 times 10 to the minus 5. So we'll start just by calculating the pH of the buffer, then calculate what happens to the pH of the buffer after we add 0.011 moles of strong base, and then once we add 0.016 moles of strong acid. All right, let's first calculate the pH of just the buffer, and in order to do that, I'm going to use the Henderson-Hasselback equation, which requires me to know the concentrations of the acids and bases. Starting with the base, I have 25 grams of ammonia. The molar mass helps me to get the number of moles, 1.47 moles. in 1.75 liters. That's important, which gives me a concentration of 0.840. So over here for base, you see 0.840. The acid, which comes from the ammonium chloride, NH4Cl, we have 45 grams of it. The molar mass is 53.5 grams per mole, which is 0.841 moles in 1.75 liters, gives me a concentration of 0.481 molar acid, which you see reflected here. We're told that the Kb is 1.8 times 10 to the minus 5, so we can substitute that here for Kb. The rest of this is just a calculation that we're very familiar with. We find the pOH and then the pH to be 9.5. Part B, calculate the pH of the buffer after the addition of 0.011 moles of sodium hydroxide. So sodium hydroxide is a strong base, which is neutralized by our acid NH4+. And remember that when these neutralization reactions occur in buffers, all of the addition of strong base is neutralized. So we know our number of, this is the number of moles before. So go back one slide and just compare the number of moles. All of it is neutralized. All of the strong base is neutralized. Here's what we're remaining with in terms of moles after the neutralization. This will become important in the next step when we talk about equilibrium. All right, so once the neutralization occurs, equilibrium is reestablished. So here's our equilibrium reaction shown. These are our initial concentrations, not moles, but concentrations. And this dissociation will occur, NH3 to NH4+. So we have change of X. Remember that this change is very small as it relates to the initial concentration. So you could use a Kb expression to find the hydroxide concentration and then the pOH and pH. But I have chosen instead to use the Henderson-Hasselback equation, where pOH is the minus log of the Kb plus the log of the acid, 0.474 over the base, 0.846. And again, the initial concentrations are calculated from the moles in the previous slide. So that gives me pOH of 4.5 and a pH of 9.50. All right, finally in part C, what happens to the pH of the buffer? Let's calculate the pH of the buffer after the addition of 0.016 moles of a strong acid. So that strong acid is neutralized by the weak base in the buffer to produce the conjugate acid NH4+ in this case. So before any neutralization occurs, we have our initial numbers of moles. Can go back and look at part A for these calculations. We neutralize all of the acid, right? That's the cool thing about a buffer. It neutralizes all the acid. In doing so, it consumes that amount of base and produces that amount of the conjugate acid. So this is our number of moles after the neutralization. After we know the number of moles after the neutralization, we can find the concentration. And that would be our initial concentration here in this equilibrium step. This is the moles from the previous slide divided by 1.75 liters, okay? And then I use the Henderson-Hasselback equation to find the pH. So pOH is pKb, or minus log of the Kp, plus the log of the acid concentration at equilibrium, which is 0.490. Remember, this is very small, over the base, which is 0.831. That gives me a pOH of 4.5 or a pH of 9.50. Problem 5, AP style free response. We have lactic acid, HC3H5O3, a monoprotic acid that dissociates in aqueous solution as represented by the equation shown. Lactic acid is 1.66% dissociated in 0.50 molar HC3H5O3 at 298 Kelvin. Assume a constant temperature of 298 Kelvin. A, write the expression for the acid dissociation constant Ka for lactic acid and calculate its value. B, calculate the pH of 0.50 molar lactic acid. C, calculate the pH of a solution formed by dissolving 0.045 moles of solid sodium lactate in 250 milliliters of 0.50 molar lactic acid. Assume the volume change is negligible. D, a 100 milliliter sample of 0.1 molar HCl is added to 100 milliliters of 0.5 molar lactic acid. Calculate the concentration of lactate ion in the resulting solution. All right, so part A, write the expression for the acid dissociation constant Ka for lactic acid. So we know that the hydrogen ion concentration and the lactate ion concentration are equal. You can see that from this equilibrium chart I made, where the dissociation of 0.5 molar lactic acid results in a final amount of X for both the hydrogen ion and the lactate ion. We are also told in the problem that the lactic acid is 1.66% dissociated. So in a 0.5 molar concentration solution of lactic acid, 1.66 of it are the ions, which is 0.0083. Okay, so Ka is hydrogen ion concentration times lactate ion concentration, which we're told is 0.0083 over the 0.5 molar lactic acid concentration. Remember that this change is very small compared to the initial concentration, so we can assume the change is negligible and use the initial concentration here. In doing so, we get a Ka of 1.4 times 10 to the minus 4. Part B, calculate the pH of the 0.5 molar lactic acid solution. So in the previous part, we found that the hydrogen ion concentration was 0.0083. We can use that to find the pH. Minus log of that concentration is 2.08. Part C, calculate the pH of solution formed by dissolving 0.045 moles of solid sodium lactate in 250 milliliters of 0.50 molar lactic acid. Assume volume changes are negligible. So, a couple steps here. We're initially starting out with a concentration of 0.5 molar lactic acid and 0.18 molar lactate ion. That comes again from 0.45 moles in 250 milliliters, okay, to get that concentration. We dissociate some of the acid into its ions, and we have these concentrations at equilibrium. Concentration of the hydrogen ion is X, and the lactate and lactic acid are approximately equal to their initial concentrations. We have a Ka expression that we can write, H plus times lactate ion concentrations over lactic acid allows us to find the hydrogen ion concentration, again, just substituting these values, equal to 3.4 times 10 to the minus 4. Once we know the hydrogen ion concentration, we can calculate the pH to be 3.41. We don't have to go through all of those equilibrium steps if we don't want to, as long as we remember that we can use the Henderson-Hasselback equation, since we have a solution of weak acid and a salt containing its conjugate base, in this case lactic acid and lactate. So pH is the log of pKa 1.4 times 10 to the minus 4, which is which was calculated in part A, plus the log of the concentration of the base, which again is 0.045 moles per 250 milliliters, over the acid, which is given as 0.50 molar. In doing that, we calculate the same pH of 3.41. Part D, a 100 milliliter sample of 0.10 molar HCl is added to 100 milliliters of 0.5 molar lactic acid. Calculate the concentration of lactate ion in the resulting solution. In this case, the volume of the solution is doubled from 100 to 200 milliliters for both the 0.1 molar HCl and the 0.5 molar lactic acid, cutting their molarities in half to 0.05 molar HCl and 0.25 molar lactic acid. So you can see those initial concentrations reflected there. HCl is a strong acid, so it will completely dissociate, yielding 0.050 molar H+. If we assume that X is very, very small, then the hydrogen ion concentration is just equal to the 0.050 completely contributed from the HCl. And also, our initial concentration of lactic acid can be assumed to be approximately equal to its initial concentration, 0.25. The lactate ion concentration then is just equal to X. Now, our Ka expression is the same as before. Our Ka value is the same as what was calculated before. I'm just rearranging now to find the lactate ion concentration of 7 times 10 to the minus 4.